So, my dear students, so let us continue the last session, that is the coordination compounds. So, in the last class, we already completed up to the nomenclature of coordination compounds. That you have already seen the nomenclature of many complexes. So, you have seen the rules which are given by IUPAC, like there are for the neutral complexes, cationic complexes, anionic complexes. These are all different rules you have already completed in the last session. Now, let us continue the coordination compound after this nomenclature. So after this nomenclature, the first the theory which is very famous and which is very easier to understand and which is very interesting, this the Werner's theory. So you have to understood this. So this Werner's theory is nothing but this is a theory which explains us the bonding nature between the metal and ligand. So now you know that generally we are having what is actually complex means. Complex is nothing but a metal which is coordinated with ligand, and this ligand must have the lone pair of atoms so that these lone pair of atoms can donate their electrons to their vacant d orbitals of this metal, and it forms a certain complex. But at earlier stages, starting stages, so Werner, he is the first scientist. He tried, he did some experiment, he did some research on this particular complex, and he told certain postulates, certain statements about the metal ligand bonding. So he given some postulates about the metal ligand bonding nature, that is nothing but the complexes, how the complexes will be formed here, what actually the bonding nature between this metal and ligand. He explained, he given some postulates. So let us understand those things of this Werner's theory. So you must understand this Werner's theory. This Werner's theory is particularly about the complex. So this is one complex, this is a one complex. You know that what actually these complexes are. What is the name of this complex? That is here potassium. So first you should write only the cation. So here plus 3 is there, because 3 potassium is there, then definitely it is minus 3. Then what is the oxidation state of this iron? Simply this is the cyanide, which is minus 1 oxidation state. Generally you can directly calculate like 6 minus 3, that is plus 3, that the iron is which is having plus 3 oxidation state. Here also you can easily calculate, here minus 3, 3 chlorines are there, that means here plus 3. Here the ammonium is 0, that is 0 plus 3, here also plus 3. So what is the name of these two complexes here? So what actually these two complexes named here? Simply this is potassium hexacyano. You can write like this, potassium. Sorry, 1 minute. So that is potassium hexacyano. This the iron, which is iron. We can this is a anionic complex or cationic complexes. You know that the complex which is having the metal, and this complex, you know that this is the minus 3, that means this is the anion. So you must write like this, ferrate, because the suffix of the anionic complex will be 8, ferrate, like this. So ferrate, what is the charge of the iron, which is again plus 3. Like this, you should give the name of this particular complex. And here also you should give the name like this. So here first cation, this is a cation, this is our anion. So that means here, so we can write like this, hexaamine, hexaamine, and next the cobalt here, cobalt, and here the oxidation state will be 3 and chloride. So this is the name for this particular complex. So these all things you have already studied in the last session, that is the nomenclature. But you need to understand this Werner's theory, what actually the Werner's theory. So let us understand these things. So see here. So let us understand these things. So what actually the postulates are, postulates of this. So let us think, the Werner, he is given certain statements about the metal complex. So what actually he said? So you can easily understand here. So he said first, in a coordination compounds, metal atom exhibit two types of valencies which are called primary and secondary valency. So he told that first, if any complex, definitely the complex will have a primary valency and also the secondary valency. Definitely the valency, which is primary valency and the secondary valency. That means a metal ligand, the complex must have a primary and secondary. Both the valencies are there. So what actually the valency that we will understand here. So there will be two types of valencies are there that you must understand here. So the first, which is a primary valency, and what actually primary valency. Let us see here. And this is a secondary valency, and this primary valency, which is also called principal valency, and the secondary valency, which is auxiliary valency. So what actually it is, let us understand here. So first let us read this point so you can easily understand this thing. So first one, which is, it is the valency which satisfy the oxidation state of a metal. So it is a valency which satisfy the oxidation state of metal, and this is a primary valency. Remember that this is a principal valency or primary valency which must satisfy the oxidation state of a metal, and it is an ionizable valency, and it is non-directional valency, and it is not specific, it may change. It is written after the coordination outer sphere, and it is shown in with the dotted lines. Simply it denotes the charges and the complexes. Let us understand these things here. So see here, simply it denotes the charges and the complexes. So let us understand the last one. See this. So you can easily understand here, that is, see here. So what actually you can see here, this is our complex. So what actually here, so how can we write here charges here? Here we can write as +3 here, and here we can write -3 here. That's it. You know that this is the anionic part and this is a cationic part. Cationic part here. So this is our anionic part. Sorry, this is our anionic part and this is our cationic part. And here also up to here, and this is the cationic part +3, and here this part will be -3. That is the anionic part. So you can easily understand that the primary valence is nothing but which satisfies the oxidation state of central metal ion. So you can easily understand here. So the coordination sphere, ఏదైతే coordination sphere ఉంది నాన్న, దీని ఏమంటారు? Coordination sphere అంటారు. So I already told you in the last session, that is the coordination sphere. ఇక్కడ నుంచి ఇక్కడికి దీన్ని ఏమంటాము అంటే కోఆర్డినేషన్ స్పియర్ అంటున్నాం. కోఆర్డినేషన్ స్పియర్. సో ఈ స్పియర్ కు బయట ఉన్నది ఇది. ఈ స్పియర్ కు బయట ఉన్నది ఉంది. So you should understand those things here. So whatever the atoms, ligands, the species, chemical species present in this will form our dative bond. అవి మాత్రమే మన dative bond form చేస్తాయి. And ఇక్కడ కూడా ఇవి మాత్రమే it can produce our dative bond, that is a coordinate covalent bond. But what about the outside of this sphere? So ఈ coordination sphere కి బయట ఉన్న పరిస్థితి ఏంటి? What actually this outer chemical species? And you know that this is our primary valency. This is our primary valency. Why? Because it will satisfy the oxidation state of central metal ion. How can we say that here? So if it is +3, then definitely it is -3, and here 6 -3 you will get +3, the oxidation state of iron. And here also this will be a -3, and here +3. That means if 3 chlorines are not there, if 3 chlorines were not there, then how can we say the charge of this particular complex, and how can we calculate the oxidation state of cobalt here? So I already told you the calculation of oxidation state. So if you know, like, let us take like this. If it is, if the chlorine, if chlorine, if it is -1, here 3 is there, that means -3, it is +3. So you can calculate in this way like this: x plus, I don't know the oxidation state of cobalt, so I'm writing x, and 6 ammonia ligands are there. The charge of the ammonia, which is 0, and here the total charge of this complex, here the complex will be +3, and x plus 0 is equal to +3, then x is equal to +3. So in this way we can calculate the oxidation state. But if chlorine is not there, how can we write, how can we calculate the oxidation state of this cobalt? That means here this chlorine, whatever the 3 chlorines, they are satisfying the oxidation state of this central metal ion. Now these chlorines, whatever the 3 chlorines, are called our primary valency, and they are outer to this coordination sphere, and they are called primary valency, and they are called primary valency. Here 3 potassium and here 3 chlorines are our primary valency. and they are ionic part. They are completely pure ionic. So Werner, he is the first scientist. He told that the whatever the outer species, they are not involved in the dative bonding, and they are completely pure ionic. So they are completely pure ionic, and these three ions. So whatever the three chlorines, so they will satisfy the oxidation state of central metal ion. So you should understand one thing here, that so the primary valency is nothing but outer to this coordination sphere, outer to the coordination sphere. So here also outer will be coordination sphere. The outer valency, which is also called primary valency. Here three is a valency, the primary valency here. Here also three is our primary valency. Let us understand those points here. So first, you should understand that it will satisfy the oxidation state of this central metal ion. So that you must understand first point. Then after that, so you can see here. So it is an ionizable valency. You can easily understand all these things. So it is an ionizable and non-directional valency. It is not having a particular direction, and it is not specific. It may change. So it will change. How it will change, I will tell you exactly. And it is written after the coordination sphere. Coordination sphere को बाइटर आसन. It is written after the coordination sphere. You should write only outer to the coordination sphere, because they are completely ionic bonds. They are not dative bonds. They are not involved in a coordinate covalent bond. So they are ionic bond. So they are ionic bond means, so they are written after the coordination sphere. They shown in the dotted lines. So you must draw the those ligands with the dotted lines, because they are not dative bonds. They are not perfectly dative bonds. So you should write in a dotted lines. Simply it denotes the charges and the complexes. It denotes the charges and the complexes. So let us understand here. So that those points you should remember that. So if you, let us take like this. See here. So you should understand here. So you should understand one thing here. See here. So here we are having this particular complex that is like this. So you should understand that this particular outer to this coordination sphere, this is our ionic part, that is +3, and here -3. Simply you can easily understand that. So this will indicate the charges and the complexes. So the complex, the charge of the complex is +3, and the charge of the metal is +3. Remember that the charge of a metal is +3, and the charge of the complex is -3 here. And here the charge of the complex is +3, because it is -3 chlorine, then it is +3, and cobalt, which is also having +3 oxidation state. Here the charge of the metal, here the charge of the metal, and the charge of the complex is only +3 here. But here it is different. The charge of the metal is +3, and the charge of the complex is -3 here. So you should understand these things. The primary valency, which will indicate the charge of the complexes. And if when you write the structure of this, you can write like this. So definitely it is our octahedral structure, FeCN6. So that means like this: Cn, 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 and this is our octahedral structure like this. This is our octahedral structure, and we have completed up to here. What about the K3? How can we write K3 here again? Here also you can write here CO, and you should draw all those ammonia molecules like this: NH3, NH3, and NH3, and NH3, NH3, NH3. So you have written all the octahedral complexes, 6 ligand. But what about this chlorine? How can we write this chlorine? How can we write here K3? So you should write these primary valencies. Here the primary valencies here, which is K3. ఇక్కడ 3 అనేది primary valency. ఇక్కడ chlorine అనేది primary valency. They are the ionic part. So you should write in a dotted lines like this. Wherever you can write here also. You can write anywhere here. So here these 3 chlorines are there. So you should write dotted lines with 3 chlorines like the here one chlorine, here one chlorine, and you can write anywhere. Here you can write 3 chlorines like this. Here also you can write anywhere K. There is no particular direction for this ionic bonds. There is no particular direction. Remember that. You can write anywhere here, but you should write with a dotted lines because they are not pure. They are not a dative bond. They are not pure coordinate covalent bond. They are simply ionic bond. So ionic actually ionic means what? So they are ready to donate their electron, ready to lose their electron to form as a cation. And if it is readily gain the electron, definitely it will be a anion here. So you can easily understand here the chlorine which is minus here, minus 1 here. Here the potassium which is plus 1 here. That means this potassium is losing its electron. And here the chlorine which is gaining its electron. So after gaining here, so here after gaining and here it after losing. So it is producing the charges. And these charges you can write anywhere here. So this chlorine and this potassium, this is called our primary valency. And remember that this primary valency is written with the dotted lines, and there is no particular specific, so there is no particular geometry for this. You can write anywhere of these three chlorines, here these three potassium ions, that is K plus, and you can write anywhere these three potassium ions and these three chloride ions. So these outer to the coordination sphere are called our primary valency. Now let us understand the secondary valency. So this is the primary valency, that is K3 and here Cl3, and they are also called principal valency. So principal valency. You should understand these things here. Principal valency. Now let us understand here. So next, let us understand this the secondary valency. So what actually the secondary valency here? Sorry. So let us understand the secondary valency now. So what actually the secondary valency? So what actually the secondary valency? So primary valency we already seen that. So this valency which satisfy the oxidation state of central metal ion, and this is an ionizable valency. This is having no direction. It is not a direction, and it is not specific. It may change. So how it will change, I will tell you here. And it is written after the coordination sphere, and it is shown with the dotted lines. It is shown with the dotted lines, and simply it denotes the charges on the complexes. Simply it denotes the charges on the complexes. That means you should understand these points about the primary valency. And here this point I will tell you here. It is not specific and it may change. So how it will change, I will tell you here. So next let us understand the secondary valency of this. So what actually the secondary valency? So what is secondary valency? Secondary valency is also called auxiliary valency. Auxiliary valency. So what actually this auxiliary valency? Let us understand here. And it is a valency which satisfies the coordination number of metal in that particular complex. So what primary valency it will give? It will satisfy the oxidation state of a metal. And now this secondary valency will satisfy the coordination number of a metal. Coordination number of a complex, that you should remember these things. So this is a valency which satisfy the coordination number of metal in a particular complex. So what actually coordination compounds? So what actually the coordination number? Simply, if you write like this, CuNH3, if you write CuNH3 taken 4 times with plus 3, if you write like this, so what is the coordination number here? The coordination number will be 4 here because 4 ligands are there. So 4 coordinate covalent bonds are there. So coordinate covalent bond ఎన్ని అయినాయి అంటే 4 ammonia molecules అయినాయి. అందుకని 4 coordination number will be 4 here. The number of ligands will be simply called as a కోఆర్డినేషన్ నంబర్. సో లోపల ఏదైతే ఈ స్క్వేర్ బ్రాకెట్ ఉంది అని అన్న కోఆర్డినేషన్ స్పియర్. సో కోఆర్డినేషన్ స్పియర్ లోపల ఉండేది సెకండరీ వాలెన్సీ, బయట ఉండేది ప్రైమరీ వాలెన్సీ. అండ్ సీ హియర్ ద పాయింట్స్ యూ షుడ్ రిమెంబర్ దిస్. అండ్ దిస్ ఈజ్ a non-ionizable valency and this is a directional valency. But before, in the primary valency, the primary valency is a ionizable valency and it is a non-directional valency. But here the secondary valency, which is non-ionizable and it is directional valency. That means we cannot produce as a positive charge, negative point, negative charge. We can't produce them like this. But in case of primary valency, we can produce the charges here. Now, but here, so in case of this particular coordination covalent bonds, that is the dative bonds, the coordination number, and they are non-ionizable and they are having a particular direction. Definitely, it is having certain direction, and it is written inside the coordination sphere. It is written in the inside the coordination sphere, and it is shown with a solid line. It is shown with the solid lines here. So, but primary valency it will shown with the data lines, but the secondary valency it will shown with the solid lines here, and it is fixed and specific. It will never change. This point you should remember that it will never change. It is fixed and it is specific. మారదు నాన్న అలానే ఉంటుంది స్పెసిఫిక్ గా ఉంటుంది దట్ ఐ విల్ టెల్ యూ హౌ హియర్ ఇట్ ఇండికేట్స్ ద కోఆర్డినేషన్ నంబర్ సో ఇట్ ఇండికేట్స్ ద coordination number. So those points you should remember that what actually the primary valency and the secondary valency, that you should remember that. So these are the points about the primary and secondary valency. So you should remember these things here. So once again I am telling you, see here. So see here. So what actually the primary valency here? So the primary valency is nothing but outer to the coordination number. This is our primary valency. And how many are there? 3 chlorines are there. That means the primary valency 3 here. Here also 3 here. Then what about the secondary valency? Again here, the secondary valency is nothing but simply the coordination number. So what actually coordination number here? The 6 ligands are there inside the coordination sphere. So it is our secondary valency. Secondary valency, that is the 6 coordination number. And here also, what is the secondary valency here? Here also 6 ammonia ligands are there. So these are also 6 secondary valency here. You can write many such examples. So if you write like this, zinc, let us take zinc NH3 taken 4 times like this. Let us take this particular complex. So how many ligands are there here? So plus 3. So sorry, how many ligands are there? 4 ligands are there. So it is our secondary valency. So this secondary valency which indicates the coordination number of a complex here, that you should remember that. So you can write any complexes like this, CuNH3 taken 4 times plus 3. You can write any such complexes here, AgNH3 taken 2 times with plus 1, that is the chlorine. So you can write like this. So here you can write Cl3, and here I am writing Cl. So what actually the primary valency in those two complexes? The primary valency in case of this, which is 3 here. This is our primary valency. And here also this 1 is our primary valency. And what is the secondary valency here? Here the 4 ligands are there. 4 is our secondary valency. Here only 2 are there. Only 2 which are secondary valency. They are our secondary valency. Those 2 points you should remember. So what actually primary and secondary? So Werner, he is the first scientist. He is the father of our coordination compound. So he is the first scientist. He did research on this particular metal complexes, and he given a statement that every metal complex is a particularly a metal complex is having two types of valencies. One is a primary valency and the second one which is the secondary valency. And always the primary valency which is written after the coordination sphere, and it is written in dotted lines, and it is ionic. But in case of second one, the secondary valency, which you should write only in a solid lines. So how can you write this particular complex? So I have already we already completed the geometry of this particular complexes. So you should write the geometry of this particular complex like this. NH3, NH3, and this is our octahedral structure. So in which, so you should remember points here. So these six ligands are our coordinate covalent bonds. Coordinate covalent bonds, which are also called dative bonds. Dative bonds here. So, but you should remember these things here. So you should remember one thing here that so see here. So now we are drawing this particular NH3 in a solid lines here. You should write only in a solid line like this. Solid line like this. Here also you should write in a solid lines. So because they are the dative bonds. But whenever you are writing these three chlorines, you should write only in a dotted lines. That is, you should write the chlorines like this. Chlorine and a chlorine. That is a chlorine. So there is no specific geometry for those primary valency. But for in case of secondary valency, the geometry is very very important. So direction is very very important. Here the three, whatever the three ammonia ligands, the direction of these six ligands is very very important, because the direction of those ligands, if it is having the direction like this, so then only the structure will be our octahedral. So here the structure will be our octahedral. So to know the geometry of complex is particularly which is a octahedral, then the ligands must be specific. The ligands must be in a that particular direction, then only you will give certain geometry. అంటే ఈ డైరెక్షన్ లో ఉంటేనే దానికి ఆ జామెట్రీ వస్తుంది, లేకపోతే రాదు కదా నాన్న. సో వాట్ ఎవర్ ద ఎవ్రీ కాంప్లెక్స్, ఇప్పుడు ఈ కాంప్లెక్స్ తీసుకున్నాను ఐరన్ FeCN6. సో ఈ Cn Cn and Cn the six cyanide ligand. So six cyanide ligands, and they are our dative bonds, and they are the secondary valency, and they are the coordination number, and they will explain the geometry of complex. They will explain the geometry of complex. That means we can say that it is an octahedral structure. We can say that it is an octahedral geometry. It is an octahedral geometry, and the direction of these ligands is specific. So it will never change. So you already know that you can change the cyanides as chlorines, as H2O, as NH3, whatever may be, but they must be six. They must be six. That means the coordination number, it will not change. Generally the whatever the secondary valency, it will never change. So you should observe, you should understand here. So here this particular complex is a 6 is our coordination number, so it will never change. So the ligands may be changed. You can write the cyanide in place of cyanide. You can write NH3, Cl, bromine, iodine, ethylene, NH3. Whatever you can write any ligands, but the coordination number will be 6. Definitely, it will never change. But in case of this is our secondary valency. But what about the primary valency? The primary valency which is outer to this coordination sphere. So this is our primary valency. And this primary valency, this is particularly this is ionic valency, and it is not having a particular direction. You can draw anywhere like this. So after completion of this secondary valency, and you can write anywhere. You can write anywhere like this. So you can write three chlorines like this, chlorine, and here three chlorine. You should write only in a dotted lines, because they are completely ionic ligands. So they are completely involved in an ionic bonding here. So this chlorine, three chlorines, we should write in a dotted lines like this. But in case of NH3, they are indicated with a solid lines. They should indicate with a solid lines here. You should understand these 2 points here. Once again, I am telling you that this outer to this coordination number, which is a primary valency, and inside of the coordination number, the ligands, number of ligands is our secondary valency. And here this is our primary valency, and the six ammonia ligands, they are the secondary valency. So you should understand those things here. The primary valency which satisfy the only oxidation state. ఇది ఏం చేస్తుంది నాన్న? Only oxidation state plus 3 అయితే ఇక్కడ -3 ఇస్తుంది అంతే. And it is a non, so non directional, దానికి డైరెక్షన్ ఏం లేదు. And this is the ionic part, and this is involved in an ionic bond. But these cyanides మాత్రం ionic కాదు నాన్న, అది అందులోనే ఉంటాయి, and బయటికి తీసుకురాలేము. They are fixed. So six ligands, it never change, but it will change. How it will change, I will tell you here. And here also same like this, three chlorines, here -3, here +3. So that you should understand these points about the Werner's theory. And let us understand again whatever the what actually how particular primary valency and secondary valency and primary valency, it will never change or it may change. So that I will tell you here. So let us understand those things again here. So see here. So let us understand here again. So we already seen what actually primary and secondary. Now let us understand these things here. So it will never change and it is fixed and specific and చెప్పినాను ఇక్కడ. Secondary valency is fixed and specific. But in case of primary valency, eh, it is not specific, it may change. అది మీకు అర్థమవుతుంది, ముందుకెళ్ళిన తర్వాత అర్థమవుతుంది. Let us see what actually he said again. So he said again, simply see here. So every metal will have a fixed secondary valency, that is the coordination number. So every metal is have a fixed secondary valency. అసలు మారదు. So that will be completely fixed. So 6 coordination number అంటే మారదు. So you can write CO, sorry, I will take another pen. So you can write like this: CO, NH3 and this 6 and here plus 3. So in place of this NH3 you can write chlorine, bromine, iodine, but you should write only 6. You should write only 6. You can write H2O, whatever maybe. You can write any ligand, but the coordination number must be 6. It will never change. It is completely fixed because it is a secondary valency. It is completely involved in a dative bonding, dative bond. Hence, so it will never change. It is 6. That is fixed. But in case of outer sphere, that is a chlorine, bromine, whatever may be, it will change. So how it will change, I will tell you here. So see here. So the geometry of the complex depends on the coordination number. Yeah, of course, definitely. The geometry of the complex will depends on only the secondary valence. You know that the secondary valency, that is the CO, NH3, and I have just now only I have written 6 like this. So here the coordination number here 6 here. So 6 is our coordination number. So you know that if you write the if you know that the coordination number is 6, then you can easily calculate, you can easily know the geometry of the complex. So if the coordination number 6, definitely the geometry will be octahedral like this. So here the ligand. So 6 ligands will make a certain geometry which is called octahedral. So what is octahedral? I already told you in the last session. You can see in the last videos. But you should understand those points here. So the coordination number which will majorly explain the geometry of the particular complex. So if it is 6, definitely it is a octahedral. Then if it is 4, so you see here, if it is 6, then the geometry is tetrahedral. That everyone knows here. But if it is 4, if it is 4, then it may be a square planar or tetrahedral, whatever may be. There is a metal and this ligand will be like this. It is a square planar. Maybe the coordination number 4, it forms a square planar, or it may be form a tetrahedral non-planar. The structure will be like this. So it may be like this tetrahedral and this is square planar. Even though both are having same coordination number, but the geometry is different. So that points you should remember here. And Werner, he also shown the cis-trans isomerism in particular planar complexes. Now, what actually the Werner told, I will tell you exactly here. So see here, once again you can see, you can easily understand here. So see here, so this is our particular complex and this is our metal ion and this is our coordination number and this is our secondary valency, and this secondary valency, this particular secondary valency, the coordination number is 6 because 6 ligands are there. And here the primary valency is this 3 chlorines are our primary valency. There 3 because 3 chlorines are there, they are the primary valency. And this primary valency which satisfy the oxidation state of a central metal ion. Yeah, of course, definitely, because here Cl3 is there, that means -3. -3 means definitely it is +3, and here which is 0, 0 plus 3, that is 3 here, the oxidation state of cobalt. So this Cl3 which will satisfy the oxidation state of central metal ion. So that you should understand here, that is our primary valency. And here the coordination number 6 means definitely it will be our octahedral complexes. So you should understand these points here. Now let us understand here. We will take some another example so you can easily understand here. Now this you can take this example: COCl3, 6 NH3 is there, and here the 5 NH3 is there. That means one NH3 is removed. So you can see here the coordination number here. So observe here. So what is the difference between this complex and this complex? So here the 6 ligands are there. 6 ammonia ligands are there, and but here 6 in here 5 ammonia ligands are there. 5 ammonia ligands are there. 1 chlorine is there. That means you should understand here The coordination number is not changing, but the ligands are changing. We can change the ligands. We change the ligands, the number or whatever the different types of ligands. So we can change the different ligands, but so the coordination number it will not change. Here the coordination number is 6, then definitely it will fix it. That is 6 is our coordination number. So you can see here, many such examples. So here also, so coordination number here, you can observe here the coordination number here. CO NH3 4, here 4 NH3 are there and 2 chlorines are there. And here also the 3 ammonia molecules are there and 3 chlorine molecules are there. That means 6 is our coordination. So 6 is our coordination number, and it is the total number of ligands, and it is our coordination number, and it is our geometry of complex. It is our geometry of complex. So we will see this. So see here. So how to write how to draw this particular structure here. So how to draw this particular structure? See here, CONH3 6, and this is our secondary valency, and this is our primary valency. The primary valency is always outer to the coordination sphere. So how to write this primary valency? You write only in a dotted line. So you can observe here. So these 3 chlorines are indicated with a dotted lines like this. So because they are primary valency, there is no specific geometry. ఇప్పుడు ఆక్టాహెడ్రల్ అని చెప్పడానికి 3 క్లోరిన్లు దాని పని లేదు. మనకి ఏం కావాలి? 6 అమోనియాలు ఉంటే సరిపోతుంది. 6 అమోనియా ligands are enough to explain the geometry of a complex that is the octahedral. So you should understand those things here. So here you should understand these things here. So 6 ligands are there. The six ligands, they will decide the geometry of a complex which is octahedral. So geometry will be like this. The octahedral, you know that the octahedral will be like this. There is central metal ion, the ligands like this, and upper one ligand and below one ligand. This is our octahedral structure. So the geometry of this particular complex, this octahedral, is decided by the 6 ammonia ligands, but not with the chlorines. So chlorines are simply, they are polar, they are ionic. I bite untai ala dotted lines tone chupetam, and they are not involved in a dative bond. But in case of the 6 ammonia ligands, they are indicated with a solid lines like this because they are involved in a dative bond here. And see here, what is the primary valency here? That is 3 is our primary valency, and the coordination number here 6 here. The secondary valency is 6, and the primary valency here 3 here. That you should understand here. But in case of the second case, you can see the second case. So here the primary valency 3 and the secondary valency which is 6. And you can observe here next, the primary valency here again 2 and the secondary valency is 6 again here. So you can take many such example. So the secondary valency, it will never change, but in case of the primary valency, it may change. It may change. So one of the chlorine here from here, it may interfere in this. So it may form like this. So you should understand those things here. So here the primary valency, it may change like this. So it may change like this. Here 3 is there, here 2 is there. That means one of the chlorine is involved in a dative bond. So one of the chlorine is involved in a dative bond. So that you should understand here. So you can take many such examples. So see here. So here also 4 ammonia ligands are there. So how we will draw this particular structures? So you can see the from first one, you can see here. So that is centrally which is a cobalt, and there are 6 ligands are there with a solid lines like this. So it is our solid lines here. 6 ammonia ligands are there. 6 ammonia ligands are there. They are the dative bond here. And after this, you should write only the dotted lines like this. 3 chlorine. You should write their primary valency. That is where the first complex is over, and you can easily read. And after this, you should understand here only 5 ammonia ligands are there. మరి ఇంకో అమోనియా ఏందన్న, ఇంకో అమోనియా మనం రాయలేదు. సో we are taking we took only the chlorine ఏదైతే తీసుకున్నామో ఒక్కదాన్ని ఇలా పంపిస్తున్నాం. సో వీడికి వచ్చి అమోనియా లేపేస్తున్నాం. ఎందుకు అమోనియా లేపాలి అంటే ఇప్పుడు NH3 ఉంది అనుకున్నాను. NH3 ఉండి క్లోరిన్ పక్కన రాదు. ఎందుకు రాదు అంటే now the coordination number will be 7. So coordination number అనేది మారదు అన్న. It is completely fixed. It is completely fixed. So it will never change. So hence one of the ammonia ligand is eliminated out. ఒక అమోనియా తీసేసి ఒక క్లోరిన్ లోపలికి వచ్చింది అన్న. Now whatever the chlorine which is come inside this, so it is having the primary valency, the character. So the primary valency and also having the ability to behave as a secondary valency. So you should see here, you can easily understand here. Here the chlorine is completely primary here, and here the ammonia ligands are secondary. But here these are again primary here, and here what about this chlorine? This chlorine is come actually from the primary valency. So here for the chlorine, for one chlorine you should write like this. So you should write the solid line here. Again you should write the dotted lines here. That you should understand here. So here you should write the solid lines here. Again you should write the dotted lines like this. Because this dotted line indicates the primary valency and this thick line indicates the secondary valency. Because that chlorine is having both the types of character here. And again again remaining 5 ammonia ligands are there. One chlorine like this and two again. They are the outer to the coordination sphere. You should write only in a dotted line like this. Here one and here one. So you should write like this. And next further you can see the many other such examples. So you can see this also example. So let us understand some another example. So you can see this example here. 4 ammonia ligands are there. So and 2 chlorines are there. One of the chlorine again entered. So here totally 6 ligands are there. So here 4 ammonia ligands. Here 1, 2, 3, and 4. So 4 ammonia ligands are there, the dative bonds. But in case of chlorine, అవి బయట నుంచి లోపలికి వచ్చినాయి నాన్న. సో అందులో రెండు మాత్రం దే విల్ ఇండికేట్ విత్ డాటెడ్ అండ్ సాలిడ్. సో ఇక్కడ డాటెడ్ ఉంది నాన్న, అగైన్ సాలిడ్ కూడా ఉంది. అండ్ హియర్ ఆల్సో ద సాలిడ్ ఉంది, అగైన్ డాటెడ్ కూడా ఉంది. But about this chlorine? This chlorine is outer to the coordination sphere. So then definitely you should write only in a dotted lines. అందుకే ఇలా dotted line లోనే రాయాలన్నా. And next you can see many such examples. So you can see the another example like this. So what actually here also you can see here. So 3 chlorines are there. So one chlorine and one another chlorine and one chlorine. 3 chlorines are again, they are actually the primary valency, but అవి మళ్ళీ లోపలికి వచ్చేసింది కదా, సెకండరీ వ్యాలెన్సీ లాగా కూడా యాక్ట్ చేస్తున్నాయి. So whenever the primary valency is acting as a secondary valency, you should write both the solid dotted lines and also with the solid line. So dotted line represents the their ionic form. They are the ionic, that may be cation or anion. So if it is solid line, we can say that they are the dative bond. So these postulates are given by the Werner. So he took only the first complex, only this. ఆయన తీసుకున్న ఫస్ట్ కాంప్లెక్స్ ఇదేనా. సో ఆయన కంప్లీట్ గా తీసుకుంది ఇదే కాంప్లెక్స్. సో ఆఫ్టర్ దిస్, సో దీని తర్వాత he took many complexes. He also seen these particular complexes. So you see here, so here 6 ammonia ligands are there and 4 chlorines are here. 4 is the primary valency, but here 6 is the secondary valency. And here now the primary valency again 3 here. Here 4 actually the primary valency. Here again 2 here, and here the primary valency 1, and here the primary valency which is 0 here. That means here the primary valency it will change here, but you can observe here the secondary valency. Here 6, 6, 6 and 6, everywhere the coordination number is 6. So remember that the secondary valency it will never change, but the primary valency it may change, but it will never change. It is no change. Asal change ana undadu ana secondary valency, that is fixed. So after this many scientists, so he also find for the platinum complex kuda he did some research. So that is first 6 ammonia ligands and the next 5, 4, 3, 2, 1. So why we should actually, why we are differentiating those particular complex? So what is the difference between those complex here? So what actually differences between this? Nothing but each complex will have some different characteristics. So that means if let us take this particular complex, let us take it is in red color and it is again in blue color, and this particular complex is in green color, and this particular complex is yellow color, and this particular complex is, so whatever maybe it may be purple like this. So each complex will show so with the different colors. So what actually difference here? So here the whatever the primary valency which is acting as the secondary valency, whenever it acts like this. So see here the in the complex, maybe each complex may be differ with their characteristic, that is a color, whatever may be. So mostly the colors will be different. So here you know that the platinum here 6 ligands are there. It may be in red color. This is also blue color, green, yellow, purple. You can see in the internet also. If you type this particular complex, you can easily understand the colors of this complex, and you can easily know many such examples. So ఈ కాంప్లెక్స్ కూడా ఇవన్నీ తీసుకున్నాను, ఒక్కొక్కటి ఒక్కొక్క కలర్ లా ఉంటుంది. ఇట్ విల్ హ్యావ్ డిఫరెంట్ కలర్స్. సో ఒక్కొక్క కాంప్లెక్స్ ఒక్కొక్కలా ఉంటుంది అన్న. Why actually those different colors here? Because the primary valency and the secondary valency is completely changing, అంతే కదా. సో మీరు అబ్జర్వ్ చేస్తే ప్రైమరీ వాలెన్సీ సెకండరీ వాలెన్సీ మొత్తం చేంజ్ అవుతుంది. సో హియర్ ద ప్రైమరీ వాలెన్సీ హియర్ 4 ఉంది. ఫస్ట్ మనకి ఎంత ఉంది, ఇక్కడ 4 ఉంది, అండ్ ఇక్కడ 4 ఉంది, నెక్స్ట్ 3 వచ్చింది, నెక్స్ట్ 2 వచ్చింది, నెక్స్ట్ 1 వచ్చింది, హియర్ 0. ద ప్రైమరీ వాలెన్సీ is 0 also, but the secondary valency here 6, here 6, here 6, here also 6, 6. Secondary valency it will never change, but the color of this complex may be, this may be red, this may be blue, this may be green, yellow, orange, whatever may be the different colors. So what actually difference between this? The primary valency is majorly difference here. The primary valency and the secondary valency, those two valencies are very important. They are given by the Werner. He is the first scientist to explain the bonding nature between this metal and ligand. సో వెర్నర్ ఆయన చెప్పిన ప్రకారం ఏంటి అంటే, ఎవ్రీ కాంప్లెక్స్ ఏదైతే మెటల్ కాంప్లెక్స్ ఉందో జనరల్ గా బయట ఒకటి ఉంది, లోపల ఉంది. సో హీ టోల్డ్ దట్ బయట ఉన్నాయి, లోపల ఉన్నాయి. సో దీని మధ్యలో ఏముంటది అంటే చార్జెస్ ఉంటాయి. ఇట్ మే బి ప్లస్ ఆర్ మైనస్. అంటే బయట ఏవైతే ఉన్నాయో హీ టోల్డ్ దట్ దే ఆర్ కంప్లీట్లీ ప్యూర్ అయానిక్. ఆయన చెప్పిన ప్రకారంగా, వెర్నర్ ప్రకారంగా, సో వాట్ ఎవర్ మే బి దే ఆర్ కంప్లీట్లీ ప్యూర్ అయానిక్. బట్ లోపల ఉన్నాయి మాత్రం ఆల్ దీస్ ఆర్ కాల్డ్ డేటివ్ బాండ్స్. So he told actually this particular part here, and you can see such example like this. So you can see many such examples. So you can see many such examples here. So this particular complex and this complex, you can take many complexes here. This is plus 3 and this is minus 3, and again this is minus 3 and this is plus 3. So you should understand those points here, the primary valency and the secondary valency. Here the primary valency is again 3 here, and here the primary valency again chlorine here 3 here, and this is our dative bond, this is the secondary valency. So this is completely about the Werner's theory, and this point you should remember each point. మీకు అర్థం కావాల్సింది ఇవన్నీ నాన్న. సో ఇవి అర్థమైతే మీకు వెర్నర్స్ థియరీ అర్థమైతే విల్ కంటిన్యూ ద next session. So first of all you should understand the even limitations also. So limitations are also very important. And what actually the limitations of the Werner's theory? So Werner's theory, what actually he told simply about the metal and the ligand. So if the complex like this and it is outer sphere is completely ionic part, that is +1, maybe -1, +2, -3. So outer to the coordination number which is ionic part, and the inner to the coordination sphere which is the secondary valency, and this is our dative bond. So Werner he told that. So but he is failed to explain the directional properties of bonds in the coordination compounds. So he failed in explaining the geometry of different complexes. So why it is having the direction which will give the geometry as tetrahedral, as graph planar. He didn't give such explanation about the geometry, and he is failed to explain why all the elements do not form the coordination compound. అన్ని ఎలిమెంట్స్ ఫామ్ చేయగలనే, మనకి ఎప్పుడు కూడా మేజర్ గా ఐరన్, కోబాల్ట్, నికెల్, మ్యాంగనీస్ ఇవే ఎక్కువ తీస్తాం. అన్ని ఎలిమెంట్స్ కావు. ఎందుకు కావు? సో ఆయన పెద్దగా ఇవన్నీ ఏం ఆలోచించలే అనమాట. సో నెక్స్ట్ యూ కెన్ సే మెనీ సచ్ ఎగ్జాంపుల్. ఇట్ డింట్ ఎక్స్ప్లెయిన్ ద నేచర్ ఆఫ్ బాండింగ్ బిట్వీన్ ద ఆయన ఎక్కువ మనకు నేచర్ ఆఫ్ బాండింగ్ ఎగ్జాక్ట్ చెప్పలేదు మెటల్ అండ్ లిగాండ్. సో బయట ఉందని చెప్పిండు మనకు. బయట క్లోరిన్ ఉంది అనుకో, ఇది -3 అండ్ +3. సో ఇక్కడ ఉదాహరణకు 6 లిగాండ్స్ ఉన్నాయి అనుకోండి, డెఫినెట్లీ ద కోఆర్డినేషన్ నెంబర్ విల్ బి 6, ద ఆక్టైడల్ అని చెప్పిండు. But what actually the difference between, what actually the bonding type between this metal and ligand? So adi andaram cheppaledu namma Werner, and he fails to explain the spectral and color properties of the complexes. So you know that every complex is particularly is a colored. It is a colored. 90% of the complexes are colored. They will show definitely color. But why they will show color? He didn't explain. And he didn't explain the magnetic property. It may be diamagnetic or paramagnetic. He didn't explain the magnetic properties of the complexes, and failed to explain the optical isomerism. Optical isomerism means that is a DL configuration, whatever maybe this comes under the stereochemistry that I will tell you later. And he didn't explain the geometry of the complex, which is a square planar or tetrahedral. That means if the coordination number is 4, then it will exhibit two types of structure. That is a square planar like this. This is our square planar, and the another one, this is metal, and this is our ligand and ligand. That is the tetrahedral. So why actually the different complexes will have tetrahedral and some other complexes will form tetrahedral? So what actually difference here? Why some compounds are producing this particular square planar geometry, and why some complexes are producing this tetrahedral geometry? So all those things, so Werner, he didn't explain all of them. He told majorly this particular thing. So majorly he told only these things here. So majorly he told only these things here that you should understand here. ఇది ఒకటి అర్థమైంది సరిపోతుంది. ఆయన చెప్పింది ఏంటి అంటే దీనికి బయట +3 ఉంటే దీనికి -3 ఉంటది. ఇది కమ్స్ అండర్ ద అయానిక్ పార్ట్, అండ్ దిస్ కమ్స్ అండర్ ద అయానిక్ పార్ట్ -3 +3, and this is our the primary valency and these are the secondary valency. Here this K3 is the primary valency and this cyanide 6 cyanides are the secondary valency. He told only these things, but he didn't explain the color properties, magnetic properties, geometry. So why it is producing the square planar geometry, octahedral geometry? He didn't explain all these things. But after Werner, there are many scientists. They did research on on those many complexes, and they found many reasons to give so this particular see here. So I will tell you exactly here. So there are many theories. So first theory, which is Werner. So Werner, he is the first scientist. So after that, there is another scientist. There is a Sidgwick. Sidgwick. He is also another scientist. So after the Sidgwick, next another theory, which is VBT theory. This is given by Pauli. So he is one of the scientists. He given this VBT theory. That is a valence bond theory. Next after that, CFT theory. This is also one of the theory. So it will explain the color property. This is also one of the property. And after this CFT, again LFT is there. That is the ligand field theory. This is also one of the theory here. So these are all different theories. So each theory will explain some postulates about the metal complexes. అంటే ప్రతి థియరీ ఏదో ఒక విషయం చెప్తానన్న. అసలు మెటల్ కి లిగాండ్ మధ్య సంబంధం గురించి ఒక్కొక్క థియరీ కొన్ని పాయింట్స్ చెప్తుంది. బట్ ఈచ్ థియరీకి కొన్ని లిమిటేషన్స్ ఉన్నాయి. సో కొన్ని పాయింట్స్ దగ్గర దే ఆర్ ఫెయిల్డ్. సో అందుకే దానికోసం అని నెక్స్ట్ కొత్త థియరీ వస్తుంది. ఇప్పుడు వెర్నర్ ఉంది, ఆయన కలర్లు కానీ కలర్ చెప్పలేదు, మ్యాగ్నెటిక్ చెప్పలేదు, సో జామెట్రీ చెప్పలేదు, స్టెబిలిటీ చెప్పలేదు. హీ డింట్ ఎక్స్ప్లెయిన్ ద స్టెబిలిటీ ఆఫ్ కాంప్లెక్సెస్. సో హీ డింట్ ఎక్స్ప్లెయిన్ ద స్టెబిలిటీ ఆఫ్ కాంప్లెక్సెస్. సో స్టెబిలిటీ చెప్పలేదు అంటే, సో హీ డింట్ ఎక్స్ప్లెయిన్ ద స్టెబిలిటీ. But after the Werner, Sidgwick, he tried to explain the stability of complexes. He given he given certain rules to calculate the stability of a complexes, and he also having certain limitations. Mali next VBD theory వచ్చింది. So next theory again CFT theory, crystal field theory, again LFT theory, like ligand field theory. So these are all different theories. They will explain the bonding nature between the metal and ligand. So one by one we'll understand all these things. So first, which is a Werner's theory, and we already completed in this session, and now we will see the next theory in the next video. And thank you for everyone.